We're now going to look at how to find the coordinates of the central points of a triangle, which should be your centroid, incenter, circumcenter, and orthocenter. If you have not learned about these central points in the Euclidean geometry chapter, this section will not make a lot of sense. Centroid was G, I, O, and H. Anyways, let's take them one by one. The centroid. You might remember that this is the meeting point of our medians, where basically medians are lines joining a vertex to the midpoint of the opposite side. So that is a median, and you can have a midpoint somewhere around, let's say here, and midpoint of this line would be somewhere around here. They all go through the same point. They would if I drew it properly. Anyways, you have your A, B, C, D, E, F, and you have that point at the center G. That's your centroid. It's the center of gravity of this figure, and it divides each median in the ratio 2:1. That's basically what we use to get the expression. Now the given vertices are x1, y1, x2, y2, and x3, y3. The coordinates of G are x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3. The x coordinate is the average of the x coordinates of the vertices, ditto for the y coordinate. And this is pretty easy to derive. All you gotta do is use the section formula to find the coordinates of D, and then use section formula again and divide AD in the ratio 2:1. You will get exactly this expression. You can try it out yourself. Let's look at incenter. As we have discussed in the Euclidean geometry chapter, incenter is the center of the incircle, which is the circle inscribed inside the triangle. There's a direct formula for this. The coordinates of I, the incenter, are the coordinates. The x coordinate is ax1 plus b x2 plus c x3 by a plus b plus c. Y coordinate is a y1 plus b y2 plus c y3 by a plus b plus c, where a is the length of the side opposite x1 y1, b is the length of the side opposite x2 y2, and c is the length of the side opposite x3 y3. This is the formula. Why does it work? It is a combination of section formula and angle bisector theorem. Let's see. So first let's draw the angle bisector of vertex A. We know that the incenter is the meeting point of the angle bisectors. So this angle bisector is AD. Let's try to find the coordinates of D. Now, because it's an angle bisector, we can apply angle bisector theorem and say that D divides BC in the same ratio as C is to B. So then we are doing section formula, and we are trying to find what is the coordinate of D, the point on BC which divides it in the ratio C is to B. That is the ratio. Bisection formula is going to be cx3. I'll write it here itself. cx3 plus bx2 by b plus c, comma cy3 plus by2 by b plus c. I think it'll be easier to just look at the x coordinate. The same thing will happen in the y coordinate, so I'm not going to bother with it. Let's just look at the x coordinate. cx3 plus bx2 by b plus c, because we have divided bc in the ratio c is to b, which is the same ratio as the adjacent sides, and that is how we do it when we have an angle bisector. Now we have to divide. Notice that, okay, let's draw another angle bisector. It is the angle bisector of vertex B. It divides AC in the ratio as the adjacent sides, but that's not what we are interested in. It divides AD. If you concentrate on the triangle ABD, there also this line is an angle bisector, and the point I divides DA in a particular ratio. But what is that ratio? For that we have to get BD is to BA. Now this BD is C by B plus C times A, while BA is just C. If you cancel the common terms, you get A by B plus C is to 1, which simplifies to A is to B plus C. So I internally divides DA in the ratio A is to B plus C. So then what are the coordinates of I? The coordinates of I would be, let's again just look at the x coordinate. A multiplied by x1 plus B plus C multiplied by cx3 plus bx2 by B plus C divided by A plus B plus C. That's the x coordinate, and you have a similar expression for the y coordinate. I'm not going to repeat myself there. B plus C and B plus C cuts, and you will see it is simply ax1 plus bx2 plus cx3 by A plus B plus C. Similarly, you will get ay1 plus by2 plus cy3 by A plus B plus C. So that is how you get it. You get it from the section formula and angle bisector theorem. Notice that this expression is very similar to the centroid expression, but not quite. Instead of finding the average of x1, x2 and x3, we found the weighted average, where the weights were the lengths of the sides opposite to them, and that's because angle bisector theorem is in play. That is the reason why this is happening.